Morning all, and here are a few loose end notes about electromagnetism that I found while I was clearing out some other notebooks. And yay, in the beginning, Hans Ørsted said that a steady electric current induces a magnetic field. So if we've got a DC current going through a wire, we'll get a magnetic field around that wire. Then a bit later on, Faraday discovered that changing the magnetic field induces a current in a wire, and that would be driven by the induced EMF. So Faraday came along, changed the magnetic field through a wire, discovered that the magnetic field changing through the wire, in other words, a varying magnetic field, or the position of the wire moving within the magnetic field, induced an EMF, which in turn induced a current in the wire. So that's sort of the opposite of Ørsted, but it's not quite the opposite of Ørsted. Then a bit later on again, Lenz came along and noted that the current that's induced by the induced EMF, by the changing magnetic field, is directed to oppose the change that created it in the first place. Now here we've got some equations. E equals minus d phi by dt. So phi is the magnetic flux, which is equal to the magnetic induction multiplied by the affected area, which, if we were speaking to the maths teachers, would look like this, and this double integral sign here means that we're integrating over an area instead of along a line. E is the EMF, got a minus sign because Lenz said the current would end up being pointed in the opposite direction, which means that the EMF has to be pointed in the opposite direction. And of course d phi by dt is the rate of change of the magnetic flux there. And if we have more than one loop of wire in our coil, then we pop in an N for the number of loops on the coil. It's probably a good idea to look at a few specific examples of how eddy currents can be used. Eddy currents are small induced currents caused by the magnetic field acting on part of a conductor. And it's important that when we're talking about eddy currents, there is not a complete circuit. Otherwise, we would just get a current that was going round and round the circuit. An eddy current is where you take a piece of a conductor that isn't a complete circuit, so a piece of metal. You vary the magnetic field across that piece of metal, either by changing the value of the magnetic field or by moving the piece of metal through the magnetic field. That, as we know, induces an EMF, and that in turn induces a current. And since the currents have nowhere to go outside of the piece of the conductor that is in the magnetic field, we call them eddy currents because they're eddying around inside that piece of metal, just like an eddy in a river or a stream. The force due to the eddy current follows Lenz's law, and two of the big applications for this are electromagnetic braking and induction heating. The fact that it follows Lenz's law means that the current must be directed so as to oppose the change that created it in the first place. So we're trying yet again to return to a previous equilibrium. In the case of electromagnetic braking, then what happens is that we have a piece of a conductor placed inside a magnetic field when we press the brake pedal, and the kinetic energy eventually gets transferred into heat energy. Because what happens is the kinetic energy will be used to place the conductor into the magnetic field. That means that the kinetic energy will transfer into first electrical energy, because when we put the conductor into the magnetic field, we'll induce an EMF, which will induce a current which has nowhere to go, so it's called an eddy current. And that current eddying around within the piece of metal, the conductor, will eventually transfer into heat energy. So, with clever engineering, we can turn via a magnetic field kinetic energy into electrical energy and then into heat energy and cause a vehicle to brake to a stop. Induction heating works in a very similar process. What we do is we put a large inductor, a coil, we pass a magnetic field through it, and we use that magnetic field to produce heating in a pan. So You have a current going through a coil that produces a magnetic field. The magnetic field extends out into the region of space immediately above the hob. That then passes the magnetic field into the base of the pan, and assuming the base of the pan is made of a conductor, so aluminium pans aren't going to work here, it needs to be a copper bottomed pan or something similar. That magnetic field varying, passing through the base of the pan, induces an EMF, which induces a current. Current's got nowhere to go because it's not a complete circuit, so it's an eddy current, and as the current eddies around within the conductor, gradually the energy is transferred into heat, and that in turn heats whatever is in contact with that pan, i.e. the food that you want to cook. The third big application of eddy currents is metal detectors, particularly the types of metal detectors that are used in doorways to catch people trying to steal things out of stores, or perhaps trying to catch maniacs taking guns into US Senate chambers, who knows. So what happens is, once again, we have two coils, one on either side of the doorway. One is called the receiver coil and one is called the transmitter coil. So the transmitter coil has a current going through it that will create a magnetic field across the doorway. As the person carrying the piece of metal, such as someone going onto an airplane with a pair of scissors, passes through that magnetic field, the following happens. So we've got a current going through the transmitter coil, which produces a magnetic field across the doorway. You or me or somebody else carries a piece of metal through that magnetic field. That means we've got a conductor passing through a magnetic field. So that takes us right the way back up here to the top. Conductor passing through a magnetic field induces an EMF in that conductor, across that conductor, which in turn induces currents in that conductor. Conductor isn't completed the whole circuit, so it's an eddy current, not a real proper current that's going around the circuit. It's a current, a small piece of current eddying around within that conductor, which means that eventually the electrical energy will turn into heat energy. But remember that, according to Ørsted, a current passing through a conductor will produce a magnetic field. So let's go back to the top of this again. We have a transmitter coil. We've got a current going through the transmitter coil, which produces a magnetic field across the doorway. We carry our piece of metal through the doorway, through the magnetic field of the transmitter coil. That induces an EMF, which induces a current, which induces a magnetic field around the piece of metal that we are carrying. And that magnetic field then induces a current in the receiver coil. And when a current is detected in the receiver coil, we can connect some electronics to that to set off an alarm. Hey presto, we have a metal detector archway.